Dear all, welcome back. Moving to the most important topic of organometallic chemistry, metal carbonyls. Metal carbonyls. In this area, from metal carbonyls, you can expect a minimum 2 questions in CSIR net exam. Okay, minimum 2 questions. Metal carbonyls. It is not an easy topic, most difficult topic in organometallic chemistry. Many new aspects that we have to discuss. Our first discussion about the bonding in metal carbonyl. Second one, IR stretching frequency. Third one, acidic strength. Fourth one, synthesis or preparation of metal carbonyls. Fifth one, reactions of metal carbonyls. Very difficult. Reactions of metal carbonyl, very because this is an organometallic chemistry chapter. Reaction similar to organic reaction, very difficult reactions. Then sixth one, IR bands or IR characterization of carbonyls. And seventh one, H1NMR spectral details. A lengthy topic. Okay, spectra here, IR bands or spectral details. So first of all, we are starting a very lengthy topic, metal carbonyls. Here we have to discuss about the bonding in metal carbonyl, IR stretching frequency, very complicated and very important. Then acidic strength, synthesis of metal carbonyl. This reaction of metal carbonyl is the most difficult part. Then IR bands or IR spectra, then H1NMR spectra. These aspects that we are going to discuss in this section. Okay, first of all, what is metal carbonyl? Metal carbonyl means complexes containing metal and carbon monoxide as ligands. Here a metal is present and your ligand is a carbon monoxide. Ligands are carbon monoxide. So compounds containing metal and carbon monoxide as ligands. They are classified into two. First one, homoleptic carbonyls, and second one, heteroleptic carbonyls. So metal carbonyls are classified into homoleptic carbonyls and heteroleptic carbonyls. In homoleptic carbonyls, all the ligands are carbon monoxide. So metal is connected to only carbon monoxide. Such complexes are called homoleptic carbonyl. For example, NiCO 4 times, nickel tetracarbonyl. Nickel is connected to 4 carbon monoxide. Or FeCO 5 times, iron pentacarbonyl. Iron is connected to only carbon monoxide. Or CrCO 6 times. Chromium is connected to only carbon monoxide. Mn2CO 10. Manganese is connected to only carbon monoxide. Okay, these are some popular examples of homoleptic carbonyls. Then second one, heteroleptic carbonyls. Metal is connected to carbon monoxide as well as other ligands. Metal is connected to carbon monoxide as well as other ligands. So for example, NiCO thrice, PF3 thrice. It's a coordination number 6, or nickel mostly form coordination number 4. So NiCO thrice, PF3, NiCO thrice, PF3. 3 ligands are carbon monoxide and 1 ligand is another ligand, PF3, trifluorophosphine. Okay, then next example, NiCO twice, PMe3 twice. These are examples of heteroleptic carbonyl. So this is a basic introduction about a metal carbonyl. In this lecture we are discussing about a metal carbonyl. In metal carbonyl a metal is present and carbon monoxide is your ligand. Okay, so there are two types, homolytic as well as heteroleptic. In homolytic all the ligands are CO. In heteroleptic other ligands are also present in addition to carbon monoxide. Okay, so homo and heteroleptic carbonyls. So the first topic, bonding. Bonding. Okay, please listen. Your carbon monoxide ligand, carbonyl ligand, similarly nitrosyl ligand, NO, carbonyl ligand and nitrosyl NO ligand, both ligands are pi acceptor ligands. Carbon monoxide and NO, both ligands are pi acceptor ligand. What do you mean by pi acceptor ligand? That means, please listen, what is the MO diagram, what is the molecular orbital electronic configuration of carbon monoxide? Carbon monoxide 8 plus 6, 14 electron. Carbon monoxide 14 electron, and you know carbon monoxide having exceptional electronic configuration. In the case of NO, no exception, carbon monoxide having exception. So what is the exceptional electronic configuration of carbon monoxide? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then exception is there. So pi 2p x2 equal to pi 2p y2. Then sigma 2p z2, sigma 2p, is it right? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2 equal to pi 2p y2. Then sigma 2p z2 and then pi star 2p x equal to pi star 2p y. This is the MO configuration of carbon monoxide. 2, 4, 6, 8, 10, 12, 14. 14 electrons are there in carbon monoxide. So pi star 2p x 0 equal to pi star 2p y 0. This is a MO configuration of carbon monoxide. Please listen. The outer molecular orbital of carbon monoxide is pi star 2p x 0 is equal to pi star 2p y 0. That means the outer pi star orbital is vacant. Outer pi star orbital is vacant. So carbon monoxide having a vacant pi star orbital. Vacant pi star orbital. So please listen. Consider this as a metal. This as a metal. And carbon monoxide is a ligand. Carbon monoxide is a ligand. Please listen, very, very important. I am metal and carbon monoxide. Okay, so carbon monoxide, in carbon monoxide, carbon is the donor. Carbon is the donor. The primary function of every ligand, donate electrons to the metal. Donate electrons to the metal. That is the primary function of every ligand, donating electrons to the metal. Okay, and this bond is called sigma sigma bond. The first bond formed is called as sigma bond. Okay, then you know this carbon monoxide having a vacant pi star orbital. Carbon monoxide having vacant pi star orbital. This is the vacant pi star orbital of carbon monoxide. Vacant pi star orbital of carbon monoxide. Clear? So when suppose the metal having high electron density. Suppose first thing is carbon monoxide will donate electrons to the metal to form a metal carbon sigma bond. Then if your metal is electron rich, if this metal is electron rich or metal having surplus electron density, or your metal is highly electron rich, then another interesting phenomenon takes place. If your metal is highly electron rich, metal having surplus electron density, metal very electron rich, then what happens? That electron density will be back donated to the vacant pi star orbital of carbon monoxide. This bonding is called back bonding. Back bonding, or it is also called as back donation, or it is also called as synergic bonding. Okay, or it is also called as what? Synergic bonding. Okay, so in first case carbon monoxide donates its electron density to metal, sigma bond is formed. Then what is back bonding? Suppose your metal is very electron rich or metal having surplus electron density. That electron density will be back donated to the vacant orbital of ligand. What is the vacant orbital of carbon monoxide ligand? Pi star orbital. Okay, what is the vacant orbital of carbon monoxide ligand? In the case of carbon monoxide, nitrosyl, alkene, all double bond, all ligands having pi bond, their vacant orbital is pi star. Okay, so carbon monoxide containing vacant pi star orbital, nitrosyl ligand having vacant pi star orbital, alkene having vacant pi star orbital. Why alkene having vacant pi star orbital? If there is pi bond, there will be vacant pi star orbital. Alkene is C double bond C. It having pi bond. Whenever pi bond is there, vacant pi star orbital is there. Carbon monoxide is C triple bond O. It is having pi bond. So definitely vacant pi star orbital is there. All ligands having pi bond having vacant pi star orbital. But in the case of carbene means metal double bond carbon. Metal double bond carbon is called carbene. And carbine is metal triple bond carbon. In the case of carbene and carbine, the vacant orbital is p pi orbital. Okay, p pi, not pi star, p pi orbital. In the case of phosphines and in the case of sulfines, for example PH3 is a phosphine, SH2 is a sulfine, SR2 is a sulfine, PH3 is a phosphine. In this case, the vacant orbital is sigma star orbit. All these are basic information that you studied in your MSc classes. Okay, so carbon monoxide, nitrosyl, alkene, such ligands having vacant which orbit? Pi star orbital. Why pi star orbital? In the MO configuration, it is having a vacant pi star orbital. And in the case of carbene and carbine, the vacant orbital is a p pi orbital that we will study later. In the case of phosphines and sulfine, the vacant orbital is a low energy sigma star orbit. Okay, so we are discussing about the back bonding. Throughout the organometallic chemistry, this back bonding phenomenon is very, very important. So what is back bonding? Tell me, what is back bonding? the primary function of every ligand, is to donate electrons to the metal to form metal ligand sigma bond. That all ligand form metal ligand sigma bond. Then if the metal is electron rich, or metal having surplus electron density, that will be back donated to the vacant orbital of ligand. That will be back donated to the vacant orbital of ligand. What is the vacant orbital of ligand? In the case of carbon monoxide, NO and alkene, that vacant orbital is a vacant pi star orbital. But in the case of carbene and carbine, that vacant orbital is a p-pi orbital. But in the case of phosphines and sulfines, the vacant orbital is a low energy sigma star orbital. Please note these points. So carbon monoxide is a pi star pi acceptor ligand because it is having vacant pi star bond. So the first bond formed is a sigma bond. The second bond formed is a pi bond. Okay, pi bond. So a pi bonding ligand is that. Okay, so this type of back donation from filled metal orbital to vacant orbital of ligand is called back bonding or back donation or synergic bonding. The condition for back donation is the metal must be electron rich or metal having surplus electron density. Then only back bonding takes place. Okay, so carbon monoxide ligand is a pi acceptor ligand. Similarly, nitrosyl is also a pi acceptor ligand. Clear? Then please listen. A complex can be represented as this is the metal. Here n ligands are there, n ligands surrounded by the metal, and this metal is connected to carbon monoxide ligand. Carbon monoxide is C triple bond O. The carbon monoxide ligand is C triple bond O. Its bond order is equal to 3. If carbon monoxide independently present, the bond order of carbon monoxide is C triple bond O, which is bond order 3. Okay. So this is a complex metal surrounded by n ligands, C triple bond O. Suppose your metal having very high electron density or metal is electron rich, and you know carbon monoxide containing vacant orbit. Which vacant orbit? Vacant pi star orbit. Carbon monoxide having vacant pi star orbit. So definitely that electron density will be back donated to the carbon. So this first bond is called sigma bond. So this electron density will be donated to carbon. Then automatically this bond shifted towards oxygen. So reversibly gives Ln metal. Already one sigma bond is there. Due to back donation, one more bond is formed, C triple bond becomes double bond O minus. Okay, triple bond become double bond O minus. Then what you can understand? What you can understand? This is back bonding. Back bonding. Metal electron density will be donated to the vacant pi star orbital of carbon. As a result of back bonding, before back bonding, metal carbon bond is single bond and carbon oxygen bond is triple bond. After back bonding, metal carbon bond become double bond, carbon oxygen bond become double bond. Okay, so write a statement. This statement is very important. Okay, then if metal electron density increases, put this arrow, metal electron density increases, what happens? Back bonding increases. Metal electron density increases, back bonding increases, comma, metal is surplus electron rich, back bonding increases. Then what happens? Metal carbon bond order between metal and carbon increases. That means single bond become double bond. When metal carbon bond order increases, stretching frequency also increases. Stretching frequency. Compare a single bond, double bond and a triple bond. More energy is required to stretch a triple bond because the triple bond is very strong. Bond order directly proportional to stretching frequency. Bond order directly proportional to stretching frequency. Higher the bond order, higher is the energy required to stretch that bond. Okay. So when metal electron density increases, back bonding increases, bond order between metal and carbon increases, then new stretching frequency of metal carbon bond also increases. Stretching frequency, new MC, stretching frequency of metal carbon bond also increases. Then bond order between carbon and oxygen. As a result of back bonding, this bond is shifted towards this side, this towards this side. So bond order between carbon and oxygen decreases. When bond order decreases, new CO, stretching frequency of carbon oxygen bond, decreases. The very important statement of back bonding and IR stretching data. Put the statement in a box and give as many star mark you can. Okay. All the organometallic is completely based on many back bonding aspects. I think now you got an idea what is back bonding. Back bonding. Normal bonding is sigma bonding. Back bonding is metal to ligand. If metal is very electron rich, then another interesting phenomena, the metal electron density will be back donated to the vacant ligand orbital. We are discussing about the carbonyls. In carbonyls, the vacant orbital is a pi star orbital. Carbon monoxide is a pi acceptor ligand. So what happens as a result of back bonding? Metal carbon bond order, single bond to double bond increases. When bond order increases, what happens? Stretching frequency, metal carbon stretching frequency, the energy required to stretch the bond increases, and carbon oxygen, as a result of back bonding, carbon oxygen bond order decreases and stretching frequency of carbon oxygen bond decreases. Stretching frequency of carbon oxygen bond order decreases. Write this statement in a box and give a triple star mark. Then write a question. Arrange the following compounds the following compounds in the order of, arrange the following compounds in the order of nu CO and nu MC. Okay, arrange the following compounds in the order of stretching frequency. Nu is the stretching frequency, carbon oxygen stretching frequency order, and nu MC order. Actually this topic is in spectroscopy, but here we are discussing in organometallic chemistry. Okay, so first question TiCO6 2 minus, second one VCO6 minus, third one CrCO6, fourth one MnCO6 plus, fifth one FeCO6 2 plus. Arrange 1, 2, 3, 4, 5 in the order of nu CO and nu MC. You have to arrange in the order of nu CO and nu MC. Okay, how you can approach this question? Here TiCO6 2 minus, VCO6 minus, CrCO6, MnCO6 plus, FeCO6 2 plus, all are hexacarbonyl. 6 carbon monoxide ligands are present. Then all are homoleptic carbonyl. That means only carbon monoxide ligand is present. Okay. Then here complex having 2 negative charge. Here complex having 1 negative charge. Here complex having 2 positive charge. So definitely this complex, this metal having high electron density. Why titanium having high electron density? Because titanium having 2 negative charge. Higher the negative charge, higher is the electron density. Here vanadium having 1 negative charge, less electron density than titanium. Here iron having 2 positive charge, that means less electron density. Suppose the electron density at titanium is electron density 1, this is electron density 2, this is electron density 3, electron density 4, electron density 5. What is the order of electron density? Whether titanium or vanadium or chromium or manganese or iron, which one having highest electron density? Definitely higher the negative charge, higher is the electron density. So electron density 1 greater than electron density 2 greater than electron density 3 greater than electron density 4 greater than electron density 5. And you know the statement, read the statement. Higher the electron density on the metal, higher is the back donation. Higher the electron density on the metal, higher is the back donation. Then metal carbon bond order increases. Metal carbon bond order increases and stretching frequency increases. Okay, when higher the electron density on the metal, higher the back donation, metal carbon back bonding, metal carbon bond order increases and stretching frequency increases. So what is the order of nu MC? Nu MC having the order 1 greater than, 2 greater than, 3 greater than, 4 greater than 5. Why? In first complex electron density is high, back bonding is high. When back bonding high, metal carbon bond order increases, stretching frequency also increases. Then exactly opposite order in the case of nu CO. When back bonding increases, nu CO, carbon oxygen bond order decreases. When back bonding increases, carbon oxygen bond order decreases. So what is the order? 5 greater than, 4 greater than, 3 greater than, 2 greater than 1. So that is the order of nu MC and nu CO. Is it right or no? This type of question definitely every time in CSIR exam, one question is based on the carbonyl stretching frequency. Carbonyl stretching frequency, this is the carbonyl stretching frequency CO, and this is the metal carbon stretching frequency nu MC. Clear? Okay, then write the next question. Always nu CO and nu MC are inversely proportional. Nu CO, stretching frequency of carbon oxygen, inversely proportional to stretching frequency of metal carbon stretching frequency. Metal carbon stretching frequency. Okay, then write the next question. Next question. NiCO4, second one FeCO5, third one CrCO6. Okay, so arrange in the order of nu CO, nu MC and nu CO. Carbonyl stretching order and metal carbon stretching order. Okay. Nickel, here oxidation state, all having 0 oxidation state. Nickel 0, iron 0, nickel 0, iron 0, chromium 0. All having 0 oxidation state. But here only 4 carbon monoxide, here 5 carbon monoxide, here 6 carbon monoxide. Here 6 carbon monoxide is present. So definitely here 4 ligand, 5 ligand, 6 ligand. These 6 ligand will donate electrons to the metal. So suppose this is electron density 1, this is electron density 1, this is electron density 2, this is electron density 3. Which metal having higher electron density, nickel or iron or chromium? Chromium is surrounded by 6 ligand. So definitely its electron density will be high. So definitely electron density 3 greater than electron density 2 greater than electron density 1. Then read the statement. Higher the electron density on the metal, chromium having the highest electron density. Then back bonding increases, nu MC increases. What is the order of nu MC? 3 greater than 2 greater than 1. That is the order of nu MC. Then what is the order of nu CO? Exactly opposite order. 1 greater than 2 greater than 3. So nu MC and nu CO are inversely proportional. When metal carbon bond order or stretching frequency increases, carbon oxygen, this is the general representation, N ligand, metal, C triple bond, O, metal having surplus electron density, that will be back donated to the vacant pi star orbital of carbon. This bond shifted towards this side. So you will get LNM, double bond C, double bond O. Okay, this is metal plus and O minus become neutral. Okay. So here, as a result of back bonding, metal carbon bond order and the stretching frequency increases. Carbon oxygen bond order and the stretching frequency decreases. That is the case. Then MO diagram of carbon monoxide. MO diagram of carbon monoxide. Already the MO diagram of heteroatomic molecules, polyatomic molecules, all the heteroatomic and polyatomic molecules that we already discussed in the chemical bonding chapter. Okay, so you are familiar with the MO diagram of carbon monoxide, but I am once again explaining that the MO diagram of carbon monoxide. You know, MO diagram, here carbon is present and oxygen is present. Okay, carbon and oxygen. What is the electronic configuration of carbon? Outer electronic configuration 2s2, 2p2. Oxygen 2s2, 2p4. Okay, 2s2, 2p4. The atomic orbitals of carbon are 2s orbital, this is 2s orbital, and this is 1 2 3 2p orbital. 2p orbital. 2p means px, py and pz. Okay. Similarly about carbon, you know carbon is more electronegative. The atomic orbitals of electronegative atom, here this is the 2s orbital of carbon, but the 2s orbital of oxygen is somewhat lower energy. Lower energy. This is the 2s orbital of oxygen. Okay. Why? The atomic orbital of electronegative atom having low energy. Okay. At the atomic orbitals of electronegative atom having low energy. So this is the 2s orbital of carbon and the 2s orbital of oxygen. Oxygen lies lower energy. Then similarly the p orbital of oxygen also having low energy. 2p orbital of oxygen, px, py, pz. Okay. Then how they form that molecular orbital? So I am representing the molecular orbital of carbon monoxide. Molecular orbital of carbon monoxide. You know this 2s orbital have a very low energy. So it exists as a non-bonding orbital, not a bonding orbital. This is non-bonding. It does not participate in bonding. So 2s orbital, non-bonding 2s. Non-bonding 2s orbital. Okay, 2s orbital of oxygen. Then this 2s orbital is spherically symmetrical and it having same symmetry as that of the pz orbital. Okay, 2s orbital and pz orbital. Pz orbital lies in the z axis and 2s orbital also having same symmetry. So this 2s orbital and here the pz orbital, which one? Pz orbital combines it to form a sigma orbital. This is sigma. Okay, same 2s, same. When a bonding orbital is formed, an anti-bonding orbital is also formed. This is sigma star. So this sigma is formed between 2s orbital of carbon and pz orbital of oxygen. Okay. Then here px and py is there. Here also px and py having same symmetry. Px and py both having same symmetry. They overlaps to form 2pi orbital. This is pi. Similarly, when a bonding orbital is formed, an anti-bonding orbital is also formed. This is pi star. This is pi and this is pi star. Two pi orbital and 2 pi star. Then here a pz orbital does not participate in bonding. That pz orbital is act as a non-bonding pz orbital. So this is the MO diagram of carbon monoxide. Carbon 2s2 px py pz. Oxygen somewhat lower energy, 2s px py pz. Okay. Then this oxygen 2s is very low energy. It exists as a non-bonding orbital, non-bonding 2s. Then 2s and pz of oxygen combine to form a sigma and a sigma star. Px and py of carbon and px and py of oxygen combine to form 2 pi orbital and 2 pi star orbital. Then this pz exists as a non-bonding orbital. So this is the order. Non-bonding 2s, sigma, pi, non-bonding, pi star, sigma star. And this non-bonding orbital have slightly anti-bonding character. Very important. This non-bonding orbital have a slightly which character? Anti-bonding character. Then you know 2s2. Carbon having configuration 2s2, 2p2. Oxygen having 2s2, 1, 2, 3, 2p4. So total how many electron? 2 plus 2, 4. 6, 10. So this 10 electrons can be arranged as like this. Non-bonding 2s2, sigma 2, pi 2, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. This is the electronic arrangement. 2, 4, 6, 8, 10. And this having slightly anti-bonding character. So what is the bond order? Bond order is equal to half into number of bonding minus number of anti-bonding. Bond order equal to half into number of bonding minus number of anti-bonding. All low energy orbitals are bonding. 2, 4, 6, 8. Okay? 2, 4, 6, 8. 8 bonding electron. That is equal to half into 8 minus this non-bonding having antibond, slightly antibonding character. So number of antibonding electron is 2. So 8 minus 2 is equal to 6 by 2. That is equal to 3. Bond order 3 means carbon monoxide exists as C triple bond O. Carbon monoxide exists as C triple bond O. So already we studied in the chemical bonding chapter this, the MO diagram of carbon monoxide. Clear? MO diagram of carbon monoxide. Okay. So please listen. This anti-bonding orbital is the HOMO. This anti-bonding orbital is the HOMO. And this vacant pi star orbital is the LUMO. So carbon monoxide having vacant pi star orbital, hence it is a pi acceptor ligand. But its HOMO is slightly anti-bonding character. HOMO having slightly anti-bonding character. It is having vacant pi star orbital, hence it is a pi acceptor. Pi acceptor. Okay. So this electron density is donated to the metal, and the electron density from the metal is accepted to the vacant pi star orbital. Okay. So that's about the MO diagram. Then my question. Please write the next question. Arrange in the order of stretching frequency. Arrange in the question. Arrange in the order of stretching frequency. Arrange in the order of stretching frequency. First question, C triple bond O plus. Second question, a Lewis acid. A Lewis acid, for example, BH3. BH3 is a Lewis acid connected to C triple bond O. Third one, simply C triple bond O. Fourth one, C triple bond O minus. So 4 questions are there. Arrange in the order of stretching frequency. That means nu CO, carbon oxygen stretching frequency. Higher the bond order, higher is the stretching frequency. This was a previous question. A BH3 is connected to C triple bond O. BH3 is a Lewis acid. BH3, BF3, BCl3, all 13th group compounds, boron family compounds act as Lewis acid. BH3, BF3, BlCl3, AlCl3. Okay, all these are Lewis acid. So arrange in the order of stretching frequency. How you can approach this question? Stretching frequency is directly proportional to bond order. Higher the bond order, higher is the stretching frequency. Stretching frequency directly proportional to bond order. You know the bond order of carbon monoxide. Bond order of carbon monoxide equal to 3. Bond order of carbon monoxide equal to 3. That you know. And also you know bond order equal to half into NB, number of bonding electron, minus number of anti-bonding electron. Bond order equal to half into number of bonding electron minus number of anti-bonding electron. Clear? So please listen. Please listen. When number of anti-bonding electron increases, what happens? Bond order decreases. When number of bonding electron increases, bond order increases. That concept you know. So please listen. The bond order of C triple bond O is 3. Here C triple bond O plus. C triple bond O plus means one electron is lost. So definitely that electron will be lost from the HOMO. And this HOMO having which character? Anti-bonding character. You know this HOMO having which character? Anti-bonding character. So when electrons are lost from anti-bonding orbital, bond order increases. Clear? This is C triple bond O plus. When the HOMO of carbon monoxide is what? Having anti-bonding character. So when electrons are lost, definitely electrons are lost from anti-bonding orbital. When electrons are lost from anti-bonding orbital, bond order will increase or decrease. When electrons are lost from anti-bonding orbital, bond order will increase. Here electrons are lost from anti-bonding orbital. So definitely bond order will increase, and definitely here bond order greater than 3. Okay. Then here C triple bond O minus. Minus means one more electron is added. One more electron is added to the LUMO, which is a pi star orbital, anti-bonding orbital. So when number of anti-bonding electron increases, bond order decreases. So definitely here bond order less than 3. Okay, then what about a Lewis acid connected to C triple bond O? Lewis acid is an electron acceptor. So when electron is accepted, here only a partial positive charge. Lewis acid accept electron. So here a partial positive charge, here complete positive charge. Complete positive charge means one electron is completely lost. Here partial positive. So if here bond order very much greater than 3, here also bond order greater than 3, because electron is lost only partially, here completely. So if here bond order greater than 3, here bond order very much greater than 3. So what is the order of bond order? Bond order of 1 greater than 2 greater than 3 greater than 4. Then what about the stretching frequency? Higher the bond order, higher the stretching frequency. So the stretching frequency order is 1 greater than, 2 greater than, 3 greater than 4. Okay, so when a Lewis acid is connected to simply carbon monoxide having bond order 3, when a Lewis acid is connected to carbon monoxide, for example BH3CO, compare the stretching frequency of C triple bond O and BH3CO. Which one having higher stretching frequency? Definitely BH3CO having higher carbon oxygen stretching frequency. Why? Because bond order greater than 3. Completely C triple bond O plus very much greater than 3. C triple bond O minus bond order less than 3. One of the previous question of CSIR net exam. So we can summarize when carbon monoxide loses electron, bond order increases because electrons are lost from anti-bonding orbital. When carbon monoxide gain electron, bond order decreases because electrons are added to anti-bonding orbital. Once again, when carbon monoxide loses electron, bond order increases. Why? Electrons are lost from anti-bonding orbital. When carbon monoxide gain electron, bond order decreases because electrons are added to anti-bonding orbital. So that is the case, very important. So a stretching frequency series for homoleptic complex. This series is very useful. This series is given in the organometallic chemistry P.D. Gupta textbook. So it is very useful. That's why I am giving you. Highest, I am writing the new CO stretching frequency order. New CO stretching frequency order. A metal having 4 plus charge or 3 plus or 2 plus connected to CO. A metal having 4 plus, 3 plus or 2 plus connected to CO having the highest new CO stretching frequency. Then C triple bond O plus, then a Lewis acid connected to C triple bond O. This is approximately equal to CuCO4 plus. This is an exception. This is actually an exception. So I am including CuCO4 plus here. Then simply C triple bond O. Okay. Then metal with single plus connected to C triple bond O greater than metal with 0, -1, -2 connected to C triple bond O. Okay, so this is the order. Stretching frequency. If you study this chart, you can easily work out the questions of homoleptic complex. Higher the positive charge, less electron density on metal, less back donation, high CO stretching frequency. Clear? That's the concept. Higher the positive charge on the metal, 4 plus, 3 plus, 2 plus, less electron density on metal, less back donation, high stretching frequency of CO. Here 0, -1, -2 charge, high electron density on metal, high back donation, low CO stretching frequency. Then intermediate the C triple bond O plus, Lewis acid connected to this one, C triple bond O, metal positive charge connected to C triple bond O. So write a question. Arrange in the order of new CO stretching frequency. Order of new CO. Arrange in the order. First question. IR CO6 3 plus. IR CO6 3 plus. Second one Fe CO6 2 plus. Then third one C triple bond O plus. Fourth one Mn CO6 plus. Fifth one Cr CO6. All these are hexacarbonyl. Then you have to account the oxidation state. Please listen. Here 3 plus charge, here 2 plus charge, here 1 plus charge, here 0. Charge is 0. You know, higher the positive charge, low electron density. Here, suppose this is having electron density 1 and this is having electron density 5. Here metal in 0 oxidation state. In which case metal having high electron density? Here high electron density, here low electron density. Why low electron density? Metal having high positive charge. Higher the positive charge, low electron density. Please read the statement. Low electron density on the metal, low back donation. Low back donation means higher the stretching frequency. That is the series. Higher the stretching frequency order. Higher the positive charge, higher is the stretching frequency. Lower the oxidation state, lower is the stretching frequency. So what is the order of new CO? Highest stretching frequency 1. Then this is 3 plus, this is 2 plus. So then 2. Then C triple bond O plus, next. So 3. Greater than MnCO plus and 0. Plus having higher stretching frequency 4. Greater than 5. So this is the order of stretching frequency. So this type of questions are very, very important. Then our next section, heteroleptic carbonyls. So including carbon monoxide, other ligands are present. Okay, then the stretching frequency order, that is our next case. So these all are about homoleptic carbonyls.